Hello students, welcome back to the classroom point. In our previous class, we have discussed the introduction part of the equilibrium where solid liquid, liquid gas and solid vapor equilibrium exist, and its conditions also we explained. So in today's class, we should learn what is the meaning of the dynamic equilibrium by taking some examples. So let's begin the class now. So the meaning of dynamic equilibrium means in the equilibrium there is a movement. Usually equilibrium exists between the reactant molecules and the product molecules. So in reactant molecules always converts into the product molecules, and product molecules always converts into the reactant molecules. But once a reaction reached the state of equilibrium, so there shall be no movement, there is no stoppage of the movement of the reactants to products and products to the reactant molecules. So once a reaction reached the equilibrium, still there is a conversion of the reactants to products and products to the reactant molecules. That means the processes will not stop. It will continuously to takes place. Only thing is they takes place with equal rate. So such type of the reversible reactions at equilibrium where both a forward reaction and backward reaction do not stop but takes place continuously with equal rates, such type of the equilibrium is known as the dynamic equilibrium. So let us take an example to understand this dynamic equilibrium in a better way. So here I am taking the some amount of the water. Take a beaker. So this beaker is having some quantity of the water. To this beaker, now let us add sugar. When sugar is dissolved into the water, automatically the solid sugar molecules dissolves and they convert into the aqueous sugar molecules, because after dissolution there is no solid sugar molecules, they are all present in the liquid form. So such type of the liquid sugar molecules in the water is called as the aqueous sugar. So that here what is happening? Sugar in solid state converting into the sugar in aqueous state. Reverse we shall fill it later. Here we need to understand one more thing regarding the saturated and unsaturated solutions. Saturated solution means, imagine in 100 ml of the water, if there is a chance to dissolve maximum amount of the 5 grams of the sugar, that means only that 100 ml of the water can take only 5 grams of the sugar. So that 5 grams of the sugar, when you add to the 100 ml of the water, it completely dissolves. After the 5 grams, if you add any extra amount of the sugar, that will not dissolve, that will be precipitated at the bottom of the flask. Such type of the solutions where no more extra amount of the solute cannot be dissolved, can be dissolved, is called the saturated solution. Means extra amount of solute cannot be dissolved. Unsaturated solutions. Unsaturated solutions means in the same 100 ml of the water, if you add 4 grams of the sugar, it dissolves. If you add 0.5 extra grams, it will dissolve. Even 0.5 grams extra you dissolve, it will dissolve until it reaches the 5 grams. Once 5 grams reaches, it becomes the saturated, so that you cannot able to dissolve any extra amount of the sugar or solute. That means, see, these are all 4 grams, 4.5 grams, these are all called the unsaturated solutions, because for 4 grams of the solution, we are able to add extra amount of the solute particles that we can dissolve. Such type of solutions are called the unsaturated solutions. Remember that concept of equilibrium is applicable only to the saturated solutions, because in saturated solutions both forward and backward reactions takes place continuously with almost equal rates. Now let's come back to the concept Here I try to dissolve some amount of the sugar. That sugar particles, imagine in the form of the dots, they dissolved into the water so that the solid sugar particles are converted into the aqueous sugar molecules. To this, now I am adding the extra, this is saturated solution. To this I am adding the extra amount of the radioactive sugar. So radioactive sugar means it has the radioactive nature of either carbon 14 or oxygen 18. Let us imagine just this radioactive sugar is having some color, let it be yellow color. So when extra amount of the radioactive sugar is added, what we can expect is these radioactive sugar particles should not dissolve into the water and they have to form a precipitate at the bottom of the beaker. But practically it was observed that after some time, these yellow colored radioactive sugar particles are appeared in both liquid as well as in solid state. So how could this happen? This is happening because radioactive sugar particles, even after the solution reaches the saturated stage, they start converting into the, they start dissolving into the solution. As we said, no more extra amount of the solute can be dissolved. That means whenever one of the undissolved solute particles try to dissolve into the solution, it has to create some space there so that already dissolved sugar particles try to come out in the form of crystals. That means here dissolution and crystallization both occurs. So that is the reason why these yellow colored sugar particles are observed in both aqueous state as well as in the solid state. So here both process continuously to takes place so that we can observe that. So here what we can observe is rate of dissolution is equals to rate of crystallization. Reaction reached the equilibrium stage, but still we are able to observe the both type of the particles in both the states. That means now aqueous sugar particles are in equilibrium with the solid sugar particles. The solid sugar particles are called as the undissolved. Undissolved sugar. This is called as the dissolved sugar particles. That means if the process is already in equilibrium, why these yellow colored sugar particles are observed in the liquid state means there is a dynamic equilibrium. Dynamic equilibrium meaning here is even after reaching the state of equilibrium, both are a dissolution process and crystallization process, means reactants to products and products to reactants. Process will not stop, but it will take place continuously but with equal speed. That's why we can say that the equilibrium is in the dynamic state. Now let us take another example of the gas in liquid, dissolution of the gases in liquid. Let us take a beaker in which you fill it with some water and close it. To this you add some amount of the carbon dioxide or oxygen, any gas. Here we need to discuss one more important point, that remember that whenever you want to convert liquid into its vapor, vapor means it is in the gas state. Entropy means disturbance in the system increases. So delta S is positive. Then liquid to vapor means you have to break the interactions present between the liquid molecules and to convert into the product molecules. So for that purpose, you need to give some amount of the energy in the form of the heat. Then only liquid will be converted into the vapor. That means here delta H, it is endothermic process, delta H is positive. Then what is delta G? Delta G may be positive or may be negative. It depends. Since the process is endothermic, So delta G becomes negative if temperature increases. If temperature decreases, delta G becomes positive. Delta G negative means the process is spontaneous. Delta G negative positive means the process is non-spontaneous. Now let us discuss opposite. Opposite in the sense, now gas you are converting into the liquid. So when your gas is converting into the liquid, obviously the disturbance in the system decreases, so that we can say that delta S, entropy of the system, decreases. Earlier we had given the heat, now you are converting higher energy particles into the lower energy particles. So obviously extra energy will be released. That's why delta H is negative. Negative means the dissolution of the gases in liquids is a exothermic process. Then what about delta G? Delta G, again it could be negative or positive depending on the temperature. So if see the process is negative here, means already it is releasing the amount of energy, exothermic process. For exothermic process, decrease in temperature will be favorable. That means lower temperature if you are maintaining, then it will be spontaneous. If you raise the temperature, it will be non-spontaneous. That means when you want to dissolve the gas into the liquid, you have to decrease the temperature. If you increase the temperature, gas will come out. That's why lower temperatures are favorable. Now come to the point here. I am sending this some amount of either carbon dioxide or water, oxygen. I am taking the carbon dioxide here. So gas particles are present in this area. Decrease the temperature. If decrease temperature will reduce the kinetic movement of the gas particles, but gas will not dissolve on its own. So some pressure is required. Imagine I am applying the mechanical pressure here. More the pressure you apply, the gas particles come closer to each other. Once they reach a sufficient time where there is no more space to come closer, automatically they have only one way to go, that is to dissolve into the liquid. That means the more the pressure you apply here, the more the gas particles dissolves into the solution. Once you stop, imagine here you applied the 1 atmospheric pressure or 2 atmospheric pressure. Let us take the 2 atmospheric pressure is applied, so that 10 gas molecules are dissolved out of 100 gas molecules. Now you stopped this. Then automatically these 10 gas molecules are in equilibrium with 90 gas molecules present which are in the undissolved state. Again, if you improve the pressure from 2 atmosphere to 4 atmosphere, imagine 20 gas molecules are dissolved. Then automatically 20 gas molecules are in equilibrium with 80 gas molecules. If you go for the 6 atmospheric pressure, then it will go for the 30 gas molecules. Imagine, so that they are in equilibrium with 70 gas particles. That means every particular pressure, at every particular pressure, a new state of equilibrium is being established. And so once you start releasing the pressure, then automatically whichever the gas particles already in the dissolved state, they start coming out into the gaseous form. That means every time the dissolved gas particles are in equilibrium with undissolved gas particles. And here also, if any radioactive gas molecules if you use, then automatically you can observe the radioactive gas particles both in the dissolved state and undissolved state. Because of the dynamic equilibrium, as I discussed, dynamic equilibrium means the process continuously takes place. It will not be stopped. Hence, reactants to products and products to reactants process continuously takes place. Now, let us see how to get these equilibrium processes. Equilibrium can be attained from both reactant side and product side. By taking the reactants, you can convert them into the products. By taking the products also, you can get the equilibrium because they will come back to the reactants. So, equilibrium is obtained by taking either of the reactant or product because it is always a reversible process. And equilibrium condition is possible only in the closed containers, not in the open containers. Reason here is, if you take open containers, imagine open container is taken. In case of open container, if you are studying the liquid gases equilibrium, the liquid converts into the gaseous state and these gas molecules try to occupy the space available for them. The entire room they occupy it. So that rate of vaporization will be faster than the rate of condensation. That means the gas molecules will not come back with the same speed of evaporation into their liquid state. So that's why in open containers it is difficult or not possible to get the equilibrium state. But if it is a closed system, then automatically equilibrium can be attained. Reason is the particles will be retained there only. So there is a more chances for the gas particles to come back to the reactant state. So equilibrium is possible only in the closed containers. All measurable properties of the equilibrium always remains constant. That means if any condition, either temperature or pressure, if any condition you are changing, here we changed. When pressure applies, every time new equilibrium is established. When pressure decreases, again new equilibrium is established. That means whenever a system is at equilibrium, if you try to change the condition, any condition, then automatically you are disturbing the equilibrium. Then equilibrium will be shifted towards either towards the reactant side or product side, depending on the type of changes you are applying there. So this particular concept we shall discuss in the Le-Chatelier principle, because that particular concept is completely based on the Le-Chatelier principle. There we shall discuss. Dear students, I hope you understand my class and we shall meet in the next class. Thank you one and all.